is a pleasure to have Catherine Potts here, back after yesterday. Yesterday we had a lecture, Introduction to Quantum Annealing by Alex Kosigi, and Q&A with Alex Kosigi and Catherine Potts. Today we will put into practice what we learned yesterday and have a software bootcamp. Catherine Potts is a mathematician. She has a PhD in mathematics with a focus on adapting machine learning algorithms to large-scale scientific imaging problems. Now she has an extremely broad background, including working with gate model machines, photonic systems, quantum annealers, and simulators to build applications for quantum computing in the areas that she has expertise in, machine learning and data-driven problems. Now she is a sales engineer at D-Wave, where she guides customers to effective use of D-Wave's quantum technology for their business problems. We are really excited having you here and look forward to today's software bootcamp. Please take it away.
Thank you everyone for having me. I'm gonna do a little bit of piggybacking on what Alex talked about last time. So yesterday, Alex introduced our Advantage quantum annealer and talked about the different ways that we use our methodology to kind of build these systems. Today, I'm going to talk a lot about our LEAP cloud-based access to these Advantage systems. We'll see the user interface in a bit, and we'll use our open source tools to build problems for the quantum annealer. So we call ourselves a practical quantum computing company, and really that means that we build our technology, our quantum computers, and also the tools that go along with the quantum computers for in-production applications. So our goal for businesses that come to us looking for solutions is that not only will they build an application for a quantum computer, but they'll use that application in their business at regular intervals. That could be daily, that could be, it could change as things kind of expand in their business, but really we want to be able to enable customers to use quantum computers at a regular interval. And so we've built tools towards that. So we'll see here, today we'll see our LEAP IDE, which is a development environment that we've built for our LEAP system. It's not the only way to access our technology. You can also use Ocean tools, which is like an open software development kit, and we'll see that as well. One of the things we'll also look at is, once you've built a problem, what does that look like in the QPU? And so we'll see that using our problem inspector a little bit later on. So our software development kit, I just kind of want to go through the different sort of layers in our software. So our software is designed to connect to, first off, our QPU, the Advantage system, but also our hybrid solvers, which involve CPUs and GPUs in combination with the QPU. So that's our base layer of our software stack. On top of that, we have samplers that actually do the connections to those computational systems. We have models where folks kind of build their problems in different sorts of ways, and we'll see that as well. And then, of course, we also have mapping methods that take things like constraints or graph problems and translate them into these models, so that then we can use our samplers to connect to the computational method. And again, this is all in the context of building, slide won't go, there it goes. Building applications on top of the software. So applications like portfolio optimization, scheduling, they may have different aspects to them. Some may be specific to optimization, some may be specific to or have a lot of constraints to them. And so all of those things are kind of, we consider those as we kind of build software to help folks build their applications. And the focus of today is building an application for D-Wave's technology. So we're gonna go ahead and we'll set the scene with a specific example. And that's going to be this example of distributed computing. So in this scenario, we're thinking about a situation where we have lots of different tasks for our system to compute. And we have a set of computers that we want to kind of distribute these tasks to. Our challenges here are that some of these tasks are related, so we can't just split them kind of ad hoc. We have to be careful about this. Some of the tasks are related. Let's say like task 7 is related to task 15. So we need information from task 7 to be able to complete task 15. So in that scenario, we'll have to pass information potentially between two computers if those two tasks aren't assigned to the same computer. Another challenge is making sure that each computer is assigned the same number of tasks. This can be modeled a couple of different ways. You can use a discrete variable set for this. And this formulation is actually an NP-hard problem. So let's look at this. So again, we're thinking about having a network of computers and a set of operations. So each computer is going to operate on one task at a time. And then if this task has a dependency on this task, then we'll have to compute this task and send information along the edge. So we're going to model this whole situation as a graph. So here is a set of 10 operations, and here is a set of 5 different computers. And we will use the operations as nodes in our graph. And then if any of these operations need information from each other, we'll model that as a dependency, which is going to be an edge in our graph, okay? Then we can think about assigning these to different computers. And I'm just going to do that by coloring the computers in certain colors and then the nodes in certain colors that match up with that computer as well. So for example, here on the orange computer, task 0 and task 2 is going to be completed. And you notice they have a dependency on each other. And then task 3 is going to be completed by the teal computer. And it also has a dependency on task 0. So we have these edges between those tasks. But since these two tasks are assigned to the same computer, we don't need to pass information between different computers for those tasks. So in that situation, we can kind of remove those edges. And that's the goal of this problem, is to find an assignment that actually minimizes the total edges in this graph that we're building. And this can be modeled as a graph K partitioning problem, where in our graph, our nodes represent operations that are going to be completed, and the edges represent messages that need to be passed between computers, or between those two operations, so dependencies in the operations. Our goal is to take this graph and partition it into sets of nodes where the number of computers corresponds to K, the number of sets that we're partitioning into. We want to make sure that these partitions are equal size, and our optimization goal is to minimize the number of edges between partitions. So I have a couple of questions, and we'll kind of go through these. My first question is, why would having different size partitions be inefficient? And we have a little bit of a B, or C here. Why would having different size partitions be inefficient? A, many more messages are passed between computers. B, memory access increases significantly across all computers. Or C, some computers have to complete many more tasks.
The answers are coming in on Discord.
Great.
There is C, there is A, there is more C. In the meantime, there was a question, is the NP hardness because of the non-linearity of connections, is what Mohammed Riza from Iran asks.
That's a good question. So the NP hardness is because of the number of different combinations that you could assign the task to. So you have to look across all of the edges and all of the potential assignments, and that's where the complexity kind of comes in, if that makes sense.
Great. Meanwhile, all answers are present, but
okay, great.
Mostly C. So
mostly C.
Yeah.
Cool. Yeah. So the answer here actually is C. If we have different size partitions, then some computers are going to have to do a lot more work than other computers, which would be inefficient, right? We want to spread the task as evenly as possible. Okay, so next question. What would happen if we maximize the number of edges between partitions? A, the system would overheat. B, we would have inefficient ordering of tasks per computer. Or C, computers would have to wait for transmitted messages before finishing tasks.
Many people are typing. There were some big C's again.
Lots of C's.
Ooh, lots and lots of C's. Oh, someone also asked, can you explain the question a bit more?
This question? Sure.
Yeah.
So remember that the edges, so each partition represents the tasks that are going to be completed on a single computer. And edges between partitions are going to represent a message that needs to be passed from one computer to another computer in order for the computer to complete a specific task. So if we have lots of edges between our partitions, if we maximize that number, what does that mean for the system?
The majority says C, but there is also A present.
Okay, A.
Oh, and what is B too?
A and B. Okay, great. Awesome. A, B, and C. So for A, we're not quite sure because we don't know exactly what the cooling mechanisms are. So I would maybe eliminate that one, but it could be a possibility. Inefficient ordering of tasks per computer. So that would be kind of within a partition how the tasks are ordered, which our problem doesn't actually address at all. So we're going to leave that one to the side as well. And then C, yes, computers would absolutely, in the worst case scenario, have to wait for transmitted messages. And in a really bad situation where we have to pass so many messages across all the time, you would have very inefficient processing of your list of tasks because task one would be on one computer, then task two would be on another computer. So you'd have to pass a message and then you'd have to pass another message to complete task three and so on and so forth. So it kind of defeats the purpose of this distributed computing, doing multiple tasks at the same time. Okay, let's go ahead. I want to jump into a little bit of a demo and we'll see our UI. So let me pull up. This is our Leap dashboard. So if you sign up for a Leap account, if you sign up for one of the free accounts, then you'll have a developer account here and you'll see kind of your name over here. And this is kind of the access that you get to our system based off of time on the QPU. So here you can select and look at how much time you've used on the different types of systems. So on this account, I've used, I have a total of 1 minute available pretty much. And you can see that if I look at my hybrid solvers, I submitted one hybrid problem. Okay. Down here, you can see a lot of things like usage statistics. You can see which solvers are online. So we have an Advantage system in Europe. We have a couple in North America, and then also our hybrid solvers as well. What I want to look at is in our resources. There we go. We have a lot of different things for folks. So you can see documentation, some interactive demos, more things about our software, but I'm actually going to look at these code examples. And here we have a bunch of different examples, and we're going to look at distributed computing. And I'm going to pull up our LEAP IDE. So you can use the IDE to do programming, or you can download Ocean tools and use whatever Python development system that you're used to build programs for the D-Wave system. If you want to use the web browser IDE, this is what it looks like. You can go ahead and look at the README file attached to this, and this kind of explains a lot about what's going on in the system. I'm going to go ahead and start this demo here. Close the README. And so our demo is starting. We're building our problem right now. We sent the problem to a hybrid solver, and we're just waiting for a little bit of a result. And as we're doing that, and there's our result here. Okay, so that's just a lot of text that doesn't mean a whole lot. Let me show you what the code did. It took this input graph here. So this graph where each of these nodes represent a task for a computer and edges represent dependencies on those tasks. And it split it into 4 different computers. So 4 different partitions. And we have a total of 3 edges going across the other partitions. So there's a lot kind of going on in our output statement. We built a graph, we built a constrained quadratic model, we talked about variables, constraints, objective, and then we sent it to the technology. So we're going to go ahead and go through that, how we build those different things.
Could you share, Catherine, is it best if everyone just watches, or is there also a way to access this notebook and follow along?
Yeah, absolutely. So you can access it. So if you sign into your LEAP account and you go to resources, and then you just scroll down to code examples and notebooks. And then if you type in distributed computing, so that's this example right here. And you can click on load in the IDE and you'll come up with this screen.
I hope someone just took a screenshot of that and can post it. Could you go back to the previous one?
Sure, right here. Yeah, distributed computing. Yep.
Right now, for everyone who is still signing up, can then find it. Thank you very much.
Yes, yeah, of course. Okay, and we're going to go through the mathematical formulation, so you'll have some time to kind of catch up a little bit with signing up for the account. Okay, so let's go back to slides. This is kind of an example of what we just saw, where our input is a graph and our output are these separated graph nodes. So again, our problem formulation, we want to minimize the number of edges between partitions, where our graph has all of the information about the tasks we want to complete and dependencies between those tasks. Our constraints are going to be that we want our partitions to be equal sizes. We talked about that. We want the computers to be working on the same number of tasks. And we also want that each node is assigned to one partition. So we want to make sure that every task is worked on by a computer. So to start off, we're going to talk about the variables that we're going to assign here. So for this problem, we're going to use binary variables. So our variables will take on a value of 1 or 0. And we'll say that the variable VIP is 1 if task I is going to be computed by computer P. So if node I, that's a task, is in a partition, that's a computer that's going to work on the task P. Our variable value will be 1 and then 0 otherwise. There's a couple of different ways you could build this problem. You could build it with integer variables, but some of the reasons why we want to use binary variables instead of integer variables is that we can enforce the constraint that we talked about where we want our partitions to have equal sizes. And if we used integer or discrete variables here, we would have some difficulty doing that. And so assigning binary variables instead of discrete or integer variables is a common mathematical tool to allow those types of constraints to be enforced in an easy way. Okay. So let's look at, let's kind of take a step back because we want to formulate our constraints next. But let's take a step back and let's think about what the situation is for a specific assignment. So again, we have 10 operations and we have 5 computers to assign operations to. And with the binary variables we just discussed, we could make an assignment that looks like this. So this is one assignment of all of these tasks to each of these computers so that the number of tasks is even and every operation is assigned to one computer. So in terms of our binary variables, this value is the value of the binary variable v3 for the operation and 2 for the computer that it's assigned to. And that's a value of 0 because task 3 is not assigned to computer 2, task 3 is assigned to computer 3. Okay? So for our constraints, what we can do in this situation is we can look at the different constraints. So specifically, each computer should have an equal number of tasks. We can look across one of the rows, so looking at each computer, and we can look and see how many tasks are assigned. So in this, the blue computer, computer 2, we have 2 tasks assigned. And if we look at like the computer 4, the white computer, we have 2 tasks assigned. And that number is specific. We can look and see that all of these computers have 2 tasks assigned. How did we get at that number? We have 10 operations and we have 5 computers. So 10 divided 5, that's 2. Okay, so there's our equal number of tasks. So we'll use that kind of looking across this row here, adding up all the binary variables gave us that number 2. So we'll use that in our constraint formulation. And similarly, if we think about the constraint that each operation should be assigned to one computer, we can look down the rows, the columns at a specific task and see that every single task, the binary variables associated with that task sum up to 1. And so that will be our second constraint. Looking down the rows, the columns. Okay, so our constraint equations then are going to look like this, where for each partition, for each computer, we sum up all the variables associated with that computer, and we want that to equal the number of tasks divided by the total number of computers that we have. So that's looking across a row. And then each node assigned to one partition, that's going to look down a column. We want for each task to add up all the variables associated with that task, and we want that value to equal 1. Okay, so now we have our constraint equations. We've decided on what our variables should look like. Next, we want to look at our objective function. And our objective function is supposed to minimize the edges between the partitions. So in general, for an objective function, our samplers are set up to perform minimization problems. So we want our objectives to have to be a minimization problem, and we want them to have linear or quadratic terms. And the general form of something like that looks like this, where here is our linear term with the binary variable qi. So ai is a coefficient on the linear term. And here we have two binary variables multiplied together. So that'll be a quadratic term with a coefficient of bij. So we want our logical objective of minimizing edges to be associated with a mathematical object that looks like this. And we can figure out what that looks like by just looking at our situation again. So in this situation, task 0 and task 3 have a dependency between them, and they're assigned to the same computer, which means that I don't need to send information between two computers for these two assignments. So that's good. On the other hand, if I look at these two tasks and the orange computer, only one of these tasks is assigned to the orange computer, which means I need to send information to the blue computer for it to be able to complete task 3. So for our objective, that's bad. We don't want that to happen, okay? So we can look at all the different possible scenarios for two tasks and one computer, and we can build a table of what all of our different possibilities could be. And that would look something like this, where operation I and operation J, if they're on the same orange computer, that's good for our two tasks and the orange computer. But if they're split across different computers in the orange computer, that's bad, because then we'll have to pass a message. But thinking in the context of the orange computer, if neither of them are on the orange computer, then we don't need to penalize situations that involve the orange computer. So that's good as well. Let's now kind of take this logical expression and translate it into the variables that we've assigned. So substituting our variable values, right, which correspond to what task is on which computer. With our variable values here, we can see that if the variable values match, that's going to be good, looking at one specific computer, so looking at the same computer P. But if they don't match, that's going to be bad for our objective function. And now we're at the point where we can kind of choose what it means for our objective function if we're in a good situation or if we're in a bad situation. And we want to add some value to the objective function. In good situations, I want to add the lowest amount that I can. So we'll add 0. In bad situations, I want to penalize that. So we'll want to add a positive value, and we'll just pick the easiest value and we'll just add a 1 there. Okay, so the value for our objective looks like this when we're in these situations logically. Now that we've built this table, we can actually use this table to fill in the general form of the objective function with the goal of finding the AI, the AJ, the BIJ for 2 operations and 1 computer. So when we do this, we can take our variable values and plug them into this expression. And we're doing that here. And then we can compare the equation to the value that it should take on. So doing that, we can simplify things. And what we get when we simplify this equation is that C equals 0 here. So we found 1 coefficient. And we can do that again, and we'll get an equation here, 1 equals AJ plus C. And we already know what C is, so this is going to tell us what AJ is. There we go. And then we can kind of go through and do the rest. So we simplify, set it equal to the value, and simplify some more. So we get that our linear coefficients are going to be 1. And we do the same thing. And this time, when we simplify this out of this equation, plugging all the values in that we know so far, we get that our quadratic coefficient is -2. So now that we have all of those items, we can, for this specific situation, looking at 2 operations and 1 computer, we can write down the minimization problem just for those 2 interactions. So we found that AI is 1, AJ is 1, and the BIJ is -2. So this is the expression just for this situation, 1 pair of operations and 1 computer. But we actually want to look at all operations and all pairs, all computers. So for all pairs, we get an expression that looks like this, where we're summing up over all the computers and all of the edges. And I wanted to point that out. We're summing up over all the edges because we're only going to look at pairs that have a dependency between them. Okay, so for example, task 8 and 9, they don't have a dependency, so we don't need to worry about minimizing an edge between them. Okay. Okay, so we built our mathematical expressions. And so now our problem formulation went from a logical situation into mathematical equations. And so that looks like this. Our graph input is the same. Here we have the minimization problem that we built for our objective and the equations that we built for our constraints as well. And I just wanted to point out like the key components of what we just did. We defined variables for our problem, and our binary variables represent which operation is being done on which computer. We defined an objective function, which is trying to distribute the work as evenly as possible. And we also defined constraints. And our constraints are going to make sure that we have evenly distributed operations and model our binary variables as discrete. So that's the restriction that we want each task assigned to 1 computer. Okay, so now that we have a mathematical expression in mind for this program, we can go ahead and map it to our the D-Wave solver. So there are some main steps to solving a problem using D-Wave technology. First off, we need to take our mathematical expression and translate it into a program using Leap and Ocean tools. Then we'll need to connect to one of D-Wave's solvers or samplers. We'll sample the problem using that connection we made, and then we need to interpret the results. So I mentioned Ocean, our software development kit, and I thought this was kind of a good time to just talk about the documentation that's available. So this is an open source Python SDK. You can go ahead and look at the Ocean documentation. Whoops, too fast. You can look at the Ocean documentation and you'll come up with a page that looks like this. So if you Google search D-Wave Ocean documentation, you should come up with a page that looks like this that talks about all of our different packages that we have. And then there's also this really handy kind of getting started guide that has a lot of really good tips for building applications and using all of these tools. But we're going to use some of them now. So we'll go through that. We're going to use a hybrid solver. We're going to use the constrained quadratic model solver, which a lot of our customers find very effective for their production scale applications. So as Alex said yesterday, this is going to be a combination of classical computing and quantum computing. We get to use a very native representation of the problem. That means the mathematical expressions that we just formulated, we will be able to see in our code and plug into the constrained quadratic models. So that's very helpful for building applications. We're able to do large application problems. We're able to incorporate inequality and equality constraints. We just built some equality constraints. You could also incorporate hard or weighted constraints, and we just built hard constraints. Also, you could use binary integer or real or continuous variables, which is very useful if for things like mixed integer problems and things of that nature. We're using binary variables. We also have a binary quadratic model solver, which is the one that can solve up to 1 million variables, which allows very large industry scale problems. But this one only uses binary variables. Okay, so we're going to go through programming essentials here, and then I'll show you where they come up in that demo. So first off, we need to define our variables. So we can define our variables first using D-Wave's DIMOD package. We'll import a binary variable type because we have binary variables. We'll go ahead and set up our partitions. So remember, we have K computers that we can assign tasks to. So there's our partitions. And then we can build a list of our binary variable types for each partition and each nodes in the graph that's already been built. So we're assuming we have a graph pre-built called G. And here is the binary variables that we're setting up, named so that they match the variables that we set up in our problem formulation. So those are VIP variables. Next, we'll set up a model. So again, from our DIMOD package, we'll import this constrained quadratic model, and that's going to hold our objective function and our constraints as well as our variables. And we can instantiate an instance of that package, module. So here's our CQM model, and we'll use that name to feed in our objectives and constraints. Next, we'll define our objective function. So remember, this is what the objective function we built looks like. And in this text, or in this code here, we'll kind of start in the center here. So in the center, we have VIP plus VJP minus 2 VIP times VJP. And that expression is here. So our variables, VIP plus VJP that we defined, minus 2 VIP multiplied by VJP here, okay? And what we're doing is we're building a list of each of these interactions for every partition and every set of edges. Okay, so we're building a large list of those. And then in our CQM object, we use the set objective function to be the sum of all of those edges, of all of those, terms that we just built. So that we build a list of terms for our objective and we add them up, and that is our objective here. Okay. Next, we'll look at constraints. So we also will use this CQM object to add constraints. And this first constraint that all of these variables need to add up to be 1 for each task, that first constraint is common enough that we have a built-in function for constraints that sum up to 1. So that looks like this. In the literature, you'll hear these types of constraints called one-hot constraints. But the goal here is that each node is assigned to exactly 1 partition. So for each node, we're going to, again, make a list of the variables that need to be added up. So that's here, VIP for P and partitions. We're summing over partitions here. And so that list is going into an add discrete function, and the add discrete function takes the list of variables that you assign it and sets it equal to 1 as a constraint. So this function is within the CQM class, and we can assign a label for which partition or which equation we're specifically looking at here. So there's our collection of node constraints. Then we have another constraint, and now this time this constraint does not sum up to 1. So we can't use the add discrete function again. And this time we'll need a couple more tools. So from DieMod, we'll import this quick sum package. And we'll build a constraint from scratch here. So this time we're inside our add constraint function. This is a more generic version of the of adding a constraint. So add constraint function will look at, again, a list of all of the variables. So summing up VIP over the nodes. So VIP over the nodes here in our quick sum package. We want that to equal, this is the logic that we're adding in here. We want that to equal the number of nodes, the total number of tasks in our graph, divided by the number of partitions we have, K here. And again, we're doing this for every partition. So for every computer we're assigning tasks to, and we can assign a label to it as well. Okay. So now we've added our constraints and we've added our objective, we've defined our variables, and we've sent all of that information to our CQM model. So next step is connecting to a hybrid solver. So for CQM models, we'll use this Leap hybrid CQM sampler. My mouse keeps on like going backwards for some reason. I don't know why it's doing that, but so we'll use this Leap hybrid CQM sampler, and we can instantiate again an instance. And this sampler name is what we'll use to actually get results from the system. And so to sample the problem, we just have one line here. The sampler that we set up using the sample CQM function, we feed in our CQM that has the objectives, the constraints, and the variables inside of it. We can add a label to the problem itself. So this will connect to the sampler and give us our results in terms of a sample set, which looks like this if you print it out. So this is the sample set that you get out. So it has binary variables and their values. So all of the variables that we assign, these are the values to them. It has energy associated with it, the number of times that specific sample occurred in the sampling, and more information, but that's kind of what it looks like. So remember, now we have to kind of take a step back and think about the problem we were trying to solve. So we'll need to do a little bit of processing to get these binary variables back into a form that makes sense for our problem. So we need to interpret the results. This is the last step that we have. So to interpret the results, there's a couple of common things that we can do. One of them is to look at feasible solutions. So a feasible solution is a solution that satisfies all of the constraints that we set out. And we have a built-in flag that you can use on the sample set to kind of filter out feasible solutions. Or you can use the constraint equations that you have and calculate whether or not for a given sample, the constraints are satisfied using those mathematical objects. We often encourage folks to do both. And then also, once we know that we're looking at a sample that satisfies the constraints we set out, we can do things like post-processing. So for example, we need to take that list of binary variables and reinterpret it in terms of the original graph that we set out. And so we can do that here, which is just filtering through solutions and splitting them up into, again, which node is associated with which partition. So that's happening here. So we look at the sample, and if our value equals 1, then we put that node in the specific partition that it corresponds to. Okay. So let's go back to the code, and we'll actually see where all of those pieces we talked about are in this program. So I'm going to look at demo.py for this program, and we can see here are the import statements that I talked about. And there's a couple of different functions here in this code because we're doing things like building these pictures and things like that. So for example, here's some information, or here's a function that builds our graph. And there's a couple of different ways to build it. This visualizes the input graph, so that's going to build this picture here. And this is what I want to focus on, our building CQM function, where again, we set up our partitions, initialize the CQM object, make our list of binary variables, add our one-hot constraints, add our custom constraint that partitions need to have equal sizes, add our objective function. So we saw all of these pieces of code, and then we return that CQM. Then we have another function that runs the CQM and collects solutions. So given a CQM and a sampler object, we can actually perform that sampling and then do that feasible filtering that I was talking about. So we return a feasible sample. And then here in this process sample function, we can take that feasible sample and process it so that we have all of the information for which task is assigned to which computer, so our different partitions, and then we can visualize the results. We can build that output graph here. So I want to run this again, and what I'm going to do is I'm going to print out our CQM object, and I'll run this again. Okay, so here is our CQM object here. So I printed it all out and it looks a little messy, but I just wanted to point out the things that we built. So we built these one-hot constraints here. So our binary, our constraints that we need everything to sum to 1 are there. These are our partition constraints. So there's our partition size that we need it to equal here. This is our custom constraint that we built. And up here, all of these terms are our objective function here. Okay, so that's everything kind of all put together in the CQM package, which went to the hybrid solver. So I want to now, so there's our kind of end results. And again, we can look at our output graph and we might see a slightly different picture. Okay, so different picture than what we had before. I want to go back to the dashboard because we ran a couple of problems. So notice I ran that problem twice. Now there's 3 problems submitted, and you can see that the amount that I had available on the QPU axis changed slightly. So I lost 0.5 seconds on my QPU time. Okay, using the hybrid solver. Okay. I'm going to go back to slides. And so that was an example where we're using a hybrid solver. So our hybrid solvers, again, combine classical optimization with quantum annealing. So I used some of my QPU time in that process. They support binary, discrete, integer, and continuous variables if we use the constrained quadratic model package, which we just saw. But we can also formulate problems direct to the quantum annealer. So like a pure quantum solver, which will support binary or Ising variables. And we can submit problems that way in the form of a quadratic, unconstrained, binary optimization problem, or QBO. So this is the problem that we had formulated. It's not quite in the form of a QBO, and there are a lot of partitions here. So I'm going to kind of take a pause and we'll look at a couple of questions because I want to kind of simplify this problem for the next part. So I'm going to ask the question, what if we only had 2 computers to distribute tasks to? How could we reduce the number of variables in our problem using just 2 computers instead of k computers? And so our options for this question are A, saying that computers can't talk to each other, B, changing each variable to represent a binary assignment between the 2 computers, or C, assigning some tasks to 1 computer by hand. So,
okay, question time. Many answers D. More B. Who dares to say
lots
something?
of B's.
Yeah.
Okay, lots of B's. Okay, great. Yeah, I agree with that one. So remember our variables talked about, right, which task and which computer it was going to be assigned to. If there are only 2 computers, computer A and computer B, we could say that a binary variable of 0 could be for computer A and a binary variable of 1 could be for computer B. There we kind of cut our need for multiple variables for each task. So that's great. That'll reduce the number of variables for our problem. Next question. If we changed each variable to represent a binary assignment, which constraint is no longer necessary? A, that our partitions are equal size, B, that each node is assigned to 1 partition, or C, both are no longer necessary.
Okay, the game is on. Several people are typing. The first answers are
Okay.
Ooh, everyone agrees so far. Does it mean the previous one was twice C? Could it be the same answer now again?
Okay, so twice C. So let's think about that.
No.
Okay.
Yeah, actually more, most people say B. There is one A.
Most people say B.
Yeah,
okay,
yeah.
okay. All right. Well, okay, so let's talk about A. Let's talk about A. Okay, so we now have binary variables. We're thinking about things in binary variables terms. What would happen if our sampler returned all 1s? What would happen? That would mean that all of our tasks are assigned to computer B, which is very inefficient. So we need to make sure that that doesn't happen. So we still want to enforce that partitions are going to be equal sizes. Okay, but let's think about let's think about B. So in a binary assignment, computer A is going to represent a value of 0. Computer B is going to represent a value of 1. Is there any way that we could get a variable back that has both 0 and 1, or neither 0 or 1? And so I'm going to say no. I'm going to say no. So we don't actually need to enforce this one anymore. Okay. So we can remove constraint B. This step is a little hard to think about. So like how I think about these things when I go through simplifying our problems, I do exactly what I just did. I think about like worst case scenario. What would happen if something returned all 1s? What would happen if none of these things happened. So I kind of go through those in my head, and that usually helps me kind of figure out, okay, what do I need and what don't I need? Okay, so we talked about simplifying our problem. Now we're just looking at two computers. So k equals 2 here. We don't need to sum up over computers anymore because now our binary variables, they don't have a p index on them. So we don't have to worry about summing over p because our binary variables are looking directly at computer A or computer B. Partitions are equal sizes. We said we still wanted this one because we want to make sure that there's still a balance between the assignments. But now K value is just 2, so we can substitute that in. So we still have this constraint, and we said we didn't need this last constraint, so we're just going to cross that one off. Okay. Okay, so we need to build a cubo, and right now we still don't quite meet the requirements for a constraint for a quadratic unconstrained binary optimization problem. We have the quadratic part, we have the binary part, but we still have this constraint. So we need to incorporate this constraint somehow in our objective function. And a common way to do that is using a penalty function. So to combine our objectives and constraints together, we can do something like this, where this portion right here was our original objective, and this portion over here is a penalty function for our constraint. So let's think about this situation. Our constraint was that we wanted all of our our partitions to have equal sizes, and we wanted all of our variables to add up to be the number of operations divided by 2. So if that happens, if this number equals exactly this number, then we have 0 in the parentheses. We add nothing to the objective function. We're happy. If these two values are different from each other, then we're going to square whatever that number is. Okay, so we're going to add a positive value to our objective function. That means our minimization problem is going to increase, which the quantum annealer is going to try and avoid doing. Okay. We also introduced this parameter gamma. So this is called, often called a Lagrangian parameter, and it is a hyperparameter for our model. So we'll have to tune that and find a good value that kind of balances the original objectives with these constraints. Okay. So that's a little bit of a cost that we have to pay. Incorporating our constraint into our objective, we have an extra parameter in our problem. Okay. Okay, so great. So here's our objective function, but we're not quite ready to submit this to the D-Wave sampler. And the reason why is because remember, our objective always needs to look like this, where we have linear terms and quadratic terms added together. And here we have a giant square. So we need to simplify this. And we're going to simplify it by multiplying out this expression. So to simplify, we'll multiply out this expression. And there's a big sum in here. So we get some gnarly looking terms. So let me walk through where these terms come from. So this is the original part over here. So we'll ignore that. Here we have a summation of VI squared. That's an artifact of taking VI squared, VI, this big sum, and squaring it. If we multiply out and FOIL out all of those objects, we'll get some objects with just the VI's squared. And then we'll also get this double sum here, where we have interaction terms between the variables themselves. We'll get 2 of them for each pair. And again, that's a product of multiplying this expression by itself. We also get some cross multiplication for this side of the subtraction multiplied by the big sum, and that's here. We'll get 2 of those when we multiply these things out, so the division by 2 disappears. And then also we'll multiply this n term by itself, and so we get this expression here as well. Okay, so those are all those expressions. We can simplify this a little bit further. One thing we can notice is that this term right here is a constant in our binary variables. So there's no binary of variables attached to this term. This is often called an offset, and we can remove it from our minimization problem because it's just like adding a 7 or another number. It's not going to affect, it's not going to be affected by our binary variables changing in the annealing process. So we can remove this. And here we can simplify this expression as well, because if we think about binary variables and what the value and the values they take on, if VI is 0, 0 squared is 0. If VI is 1, 1 squared is 1. So in this situation, VI squared is going to equal itself no matter what. So VI squared is VI, and this is really just a linear term kind of hiding in this square. So this linear term, we can actually combine with this linear term over here, and here's the quadratic term that we get from our penalty function. So all of that kind of combined, we simplify again, and we get this expression here where our linear terms are combined right here. Our quadratic term is right here, and we remove the constant term. Okay, so this is going to be the expression we can use to build our cubo. And to build the cubo, we'll put all of the linear values, the linear coefficients on the diagonal of a dictionary, and we'll put the quadratic coefficients, so these guys here, on the off diagonal. Okay, so here's our cubo formulation for a situation where we just have 2 computers, so 2 partitions. Now, we're ready to solve a cubo problem using D-Wave's technology with a direct to QPU solver. So first off, we'll need to build our cubo dictionary. Then we'll connect to a D-Wave sampler or solver. We'll sample the problem using the solver, and we'll interpret the results. So a lot of these things are the same. Our basic steps are the same here. But because we're going to connect directly to a QPU with this problem, we're going to have to look at embedding our problem onto the QPU. Alex talked a little bit about that yesterday. And we'll also need to set some parameters when we send in our problem. Specifically, right, we also introduced that gamma parameter. So we'll have that as well. So let's go ahead and look and see what that looks like in code. So I'm going to move to a different example. So from the dashboard, I'm going to go to resources again, and then scroll down to a different example. I'm going to look at our graph partitioning example. So graph partitioning. And we'll wait and see that one come up. Okay, so here's the IDE for graph partitioning. I'll go ahead and look at the README while we're doing this. So here's the README, and down at the very bottom, it has our expression. Whoops, I passed it. Here's the cubo expression, the mathematical expression that we kind of built using different variable names. So I'm going to open up this graph partitioning file, and we'll see how that's translated into a QBO. So we're importing some packages. We're going to use a different sampler than the one that we had before, and we have this embedding composite function, which is going to help us find an embedding for this problem. We have some tunable parameters. There's our gamma penalty parameter and num reads. That's going to be the number of samples that we'll get back from the QPU. Here we're building our graph, and here we're setting up our QBO dictionary. So Q, we're setting up a dictionary to use here. And then we're looking over the edges and adding, these are our linear terms right here. And this is our quadratic term here over the edges. Okay, so notice the linear terms are on kind of the diagonal, and then the quadratic terms are off diagonal. If you think about it in like the form of an array. Then, hold on just 1 second. My dog is chewing on something. Okay, sorry about that. Then for the next part, we're looking over the nodes here. And this is the linear terms. So these terms right here, where we take gamma and we have 1 minus length of the nodes. So right here. And then here, we're looking over our quadratic terms, and we're adding 2 times gamma for each of our quadratic terms. So this 2 and the gamma. Okay, so there's our QBO. We have to set a chain strength parameter, and we'll talk about that in a second as well. Here we're setting up a connection to a sampler. So we're going to use embedding composite. That's a helper function to find the embedding with the D-Wave sampler, which is going to connect directly to the Advantage QPU. And we're sampling the problem. So sampler, we'll use sample QBO with the dictionary that we set up. Then we'll assign our chain strength parameter, the number of reads that we want, and we'll get back this sample. So I'm going to go ahead and run this. And now our graph is created. And now the problem is being sent to the sampler here. And we should get a response back. And while we're doing that, there we go, valid partition found with 63 cut edges. While we're doing that, I'm going to play around with a couple of things. So gamma here is set to 80. If we set gamma really low, let's say to 1, and we run this guy again, now our penalty function isn't as strong. And we'll see what happens when we get things back. So in this function, here's the post-processing that we're doing. We're looking and deciding whether or not we got a valid partition. And in this case, we got an invalid partition. So they're not balanced anymore because our penalty cost was set too low. So we'll go ahead and set that back up to 80. And another thing I want to look at is the embedding. So I'm going to import dwave.inspector. And this is a really cool tool. It's kind of one of my favorite tools, actually, because it shows information about the sample set that you get back. So information about the response object and actually how your problem was sent to the QPU. So I'm going to set that up, dwave.inspector.show response. And I'm going to close this panel and we'll hit run again. And so again, we're setting up a graph. Sending the problem to the QPU. And then we'll get this problem inspector. I'll try that again. And here we have kind of a visual representation of our problem. I'm going to make it slightly larger. Okay, so here is the logical problem that we sent to the QPU on this side. This is a histogram of samples that we got back from the QPU. So we can look and see the energy on these different samples, how many times each individual sample occurred. Remember, we asked for 1,000. And if we toggle over here, we get a visual expression of how the logical problem was mapped to the physical problem on the QPU itself. So we can look at things like clicking on one of these nodes here brings up the chain that's associated with this single logical variable in the center here. You can see that it's very highly connected in the logical problem. And so then that problem in the physical qubits is split across 4 different qubits. So if we want to see all the connections there, we can see all the different connections that are being made in the qubits to represent all the connections that we have in our logical problem. We're getting a warning that we have some larger chains. Let's play around with our chain strength. So for example, if we set our chain strength equal to 1 and we rerun this, once it's done, it's going to reload the problem inspector. Okay. Now our problem looks a little bit different. We've got lots of different warnings here because of our low chain strength. Our solutions look a little bit different too, our histogram. If we go to our our problem on the QPU itself, and we look at one of these variables now, we see that the solution is broken. And if we, let me zoom out just a tad. And if we look at the chain for that variable, it's a little hard to see, but the spins for the qubits are rendered in blue and white. And we can see along this chain, the center nodes have both white and blue values. So the chain strength wasn't large enough to enforce that this chain all have the same either spin up or spin down value. And that's why we're getting a broken chain here. Okay, and we can see even when we did our processing of our problem, we got an invalid partition there. So I wanted to show this because this is an example. If you're using D-Waves technology, you can look at the problem inspector and kind of see maybe if you're getting an invalid solution because of maybe a hyperparameter that you're tuning, or possibly because of a chain strength issue. So, okay, let me go back to slides. And we're pretty much done here. I just kind of wanted to sum up a little bit what we've done. So we took the distributed variable problem and we saw it implemented in 2 different ways. One as a hybrid problem for D-Waves technology using the constrained quadratic model, where we were able to represent the problem in its native form, an objective problem, objective function, and constraints on binary variables. And then we also saw how to take that problem, simplify it a little bit, and then map it directly to the QPU using a QUBO. If you want to reach out and with additional information, you can definitely contact me. The Leap free sign up link is here as well. If you want to learn more about how other people are using D-Waves technology, I think that our webinars and signing up for our public events is a great way to do so. We often have customers kind of come as special guests, and they explain how they use D-Wave technology in their business or in their research. Our resource library has more of these code examples, as well as papers for different applications, D-Wave's white papers, D-Wave's published research as well. And then also our career page is linked there below. And as Alex said, we don't have many postings as of yet, but we expect in the near future that more will kind of pop up. So just keep an eye out for that. And yeah, that was it. So I'm happy to answer questions that you guys have.
Amazing. Vardan is there to field the questions to you. Thank you. Amazing workshop, Catherine.
Yes,
Thank you.
Really amazing workshop. It was a pleasure listening to you. The participants enjoyed. And the Discord is currently filled with a lot of healthy discussions. The participants are asking questions and solving their queries among themselves. That is truly wonderful.
That's awesome.
Okay, so a lot of participants are now currently typing their questions, and while they post the questions, I would like to go back a bit. And there was this a bit general question asked a little while ago. And the question is there a uniform convention to process the variety of data types and the variety of data files within a particular quantum circuit?
So we don't really operate in terms of circuits for these problems. Usually, I guess a lot of times when we build applications, we do encounter a lot of different data files and data types. But in order to connect to D-Wave's technology, those all need to be translated into one of the models that we have set up. So either the constrained quadratic model or a cubing or icing problem in order to connect to our technology, if that makes sense. Alex, do you have anything to add to that?
Yeah, just a couple things. Yeah, so usually writing some kind of program to process your data, to read it in and then transform it into the models that Catherine's talking about, that's usually part of the development cycle. So you would do that in a way that's related to the data that you have. However, if you're coming from an optimization background and you already are solving a mixed integer program, we do have a function that will read in an LP file and then solve that on a CQM solver.
Great. A couple of questions are related to the platform itself. And one of the question is that some countries, unfortunately, do not have access to the LEAP program, right? So do you have in the future some programs or something in the pipeline which could provide access to these countries as well?
Yeah, so we're constantly kind of updating the areas that have LEAP access. So I would say just continue to check back on the free accounts if you're in a country that doesn't have access right now.
Some of the participants are really having fun on the D-Wave platform, and they're asking that, is there a way for students to get more free credits on the LEAP program?
So yes, so every month, if you link your GitHub account and a public repo on your account to your developer account, maybe I can show you where that is actually. So on your LEAP account, there should be something that says like expand your access right here. If you click on that guy and you link your GitHub account and a free public repo, then your minute will what am I trying to say? You'll get a free minute every month, so it'll re-up every month. And then if you need more access, that's available for purchase, and you can email me or other just sales@dwavesys.com, and we'll kind of help you out with that.
Excellent. Another question which has been time and again asked, and I feel that it has already been answered, but just to reiterate the question, is there a proven quantum advantage realized yet, or are the various industries just happy with getting maybe I would say PQC or POC just for showcasing the future advantages?
So we have some papers that we're very proud of. However, our focus is really making sure that customers find utility in the processes that we're using. So we really want to make sure that whether something is classified scientifically as quantum advantage or not, we want to make sure that our customers are getting benefit from using our quantum systems, whether that's using the hybrid solvers or direct to QPU access. So our customers look at things like, is what we're doing now saving me money in the long term? Is what we're doing now with the quantum access improving some time component in my business? Am I getting a better solution than I was before? And all of those things are massive advantages at enterprise scale. So that's really what we focus on when we're interacting with customers, people that are using our product, is how is it benefiting them? And where can we get the most benefit for them with our products?
Absolutely, that makes a lot of sense. Some of the participants really want to learn more about D-Wave, and they're asking what should be their next steps. Are there any resources available which they could refer to?
Absolutely. We have a ton of resources. So I'm just going to pull up our website here because there's so many different resources just available on the main website, which you don't even need a Leap account to access. So I really refer a lot of people to this Learn page of our website. We have a bunch of different archived webinars, events that talk about things like assessing application for quantum or hybrid. I really like this Simon Health and Years because it had medical image reconstruction, and that's like right up my background. So that one was really fun for me. So there's lots of different recordings here that you can learn more about D-Wave and how D-Wave is being used. Other things are our resource library right here, where we have public case stories of how companies are using our technology. We also have these kind of guides that you can look at. Again, you don't need a Leap account to look at these guides. We have our white papers, things like that. So those are very useful as you kind of build applications and learn more about the company. And then publications that are related to our technology is another list. There's another giant list here. You can search for publications that have just been released by D-Wave, or just all the publications, and they're broken out by year. Let's see. And then that's not what I want. Featured applications is another fun thing. If you want to see by different industries, you can look and see different applications based off of different industries. So for example, like retail, there's our Save on Foods application, or telecommunications. There's a bunch of applications there, and each of these things kind of link to different papers, presentations, webinars, things like that. So there's we have a lot of different things just on the main website to learn more about how our technology is used. Alex, do you have any other good ones?
Yeah, maybe just one more suggestion. I also really like the links that you shared there, but if you're looking for building more hands-on skills with our technology and with like problem formulation and kind of building out, extended problems, then one good way to start is by looking at our code examples page. And then think about how would you extend the example that we already have there? You know, what additional constraints can you add to the model? What can you tweak? How would you grow that? Is there a data set out there that you could try to run this problem on? So that can be a good way to use the tools that are already there, but by extending them, you can build out your skills with working with our system. And then feel free, if you have built out something that you're really proud of and want to contribute it to our open source library, feel free to add a pull request. We love getting user contributions to that.
That are indeed a lot of resources, and I'm sure other participants would love reading them and referring to them. The best thing about our program in general, the WOMANIUM program, is that there is a huge diversity of participants involved, not only students and graduates, undergraduates, we also have professors attending this particular program. One such professor, David from the US, asked that if a special access could be granted for professors and researchers so that they could include this particular program in their academic settings.
So we have the free programs. I mean, I think for individual professors, we usually handle those sorts of things on a case-by-case basis. So feel free to reach out to myself if you want to look at something for your specific program. We can get you connected with the people that can help you out with that. Yeah.
Another question which I would like to take right now is a bit more on the technical end. And the question is from Varda from India. She asks that, what is the limit of the number of nodes in a graph for the partitioning problem that the QPU can work on? And if there is any quantum speedup that the QPU can provide for that?
Sure. So let's go back to this problem. So this problem right here that we can see on the QPU, the example that I ran has 40 nodes, and this last one had 160 edges. So this is an example where you can certainly play around and bump up the number of nodes and kind of see what happens. What we see for this particular problem is that we start to get some nodes that are pretty highly connected, which means that we have to kind of build larger chains. But in this view, you can actually see the full chip. So you can see in this simple problem, I'm only using a small portion of the chip. If I increase the number of nodes, then you would see more of the chip kind of filled out. So feel free to play around with it yourself and see exactly like how much you can add to this problem before you kind of reach the limits here. Yeah.
Perfect. So I guess there's a lot of scope to play around, right?
Absolutely.
So there are a lot of comments rolling in now that it was a great session. It was very interesting bootcamp. They had an opportunity to learn quite a lot of it hands-on. So that's remarkable. I'm just scrolling through some questions. Yeah, another question is, like, while this particular session is being recorded, is there will the slide deck be shared with the participants? Could you provide that to us?
Yeah, absolutely. Yep.
Great. And just quickly, if you could browse back to the last page where you mentioned your mail and everything, some participants would like to shoot that.
Here or my, on my slides? Yeah. Just a second. There you go.
Perfect. Great. So I guess we are near the end of the session. And while the questions are not stopping anytime soon, what we'll do is we'll just list out all the questions. I'll sort them out for you and share them over mail.
Fantastic. Sounds
Great.
good.
So
Thank you so much for having us. This was so much fun.
Absolutely. It's always a pleasure to learn from you. Catherine and Alex, both of you are so great. It was a really wonderful session. Thank you once again.